Okay, good morning everyone. Welcome to the second day of this meeting. We will start with the condensed matter section. And the first speaker is Jessica Alfonsi with quantum lattice models for the exciting state properties of graphene nanoparticles.
Okay, good morning everybody. I'm Jessica from the University of Padua. So let's start today's condensed matter session by discussing electronic properties of graphene-based systems. In particular, we'll talk about nanometer-sized stripes, also known as graphene nanoribbons. This is the outline of my talk. First of all, I will give some introductory facts about graphene research, and then I will overview the main features known for the electronic properties of carbon nanotubes and graphene nanoribbons on the basis of tight binding method, namely a single particle description. Then, after briefly reviewing the shortcomings of this approximation, I'm going to introduce you to a full many-body approach I've developed based on the exact diagonalization of the Haber model. And of course, I will show you the results I've obtained for graphene nanoribbons. In the end, I will outline possible future directions for this research work. Perhaps many of you remember that the 2010 Nobel Prize in Physics was given to Guy and Ozolo from University of Manchester, UK, for their Scotch tape exfoliation method, which allowed them to isolate single graphene sheets from bulk graffiti in 2004. And here you can see from this plot the impact of their original 2004 paper, which is located at the center of this plot, which is growing year after year in a really impressive way. So today, graphene can actually be considered the two-dimensional mother of all sp2 carbon-based systems, ranging from zero-dimensional nanostructures like graphene quantum dots or fullerenes to one-dimensional systems like carbon nanotubes and graphene nanoribbons, and of course, three-dimensional graphite stacks, which are known to us since ancient times. So you can understand that today graphene is currently one of the hottest research areas in condensed matter physics. And in this slide, I'd like to give you a brief overview of the main trends in this field. First of all, you see from this graphic that the almost exponential increase of the number of papers published about graphene after 2004. While at the same time, you can see that the research output related to carbon nanotubes experienced a decrease. So this means that within the latest decade, the focus of researchers shifted from carbon nanotubes to graphene. The leader countries in the number of publications and patents, you can see from these plots, are United States of America, China, Japan, and South Korea, while European countries seem to be experiencing a loss of competitiveness, such as UK's, as it turns out from this news taken from the Guardian newspaper. However, let's remember that European countries contribute to the papers with the highest number of citations, as it was the case with Guy and Ozolo's papers. Finally, from this plot, you can see that graphene is currently a multidisciplinary research field. However, the main focus on this material stems mainly from condensed matter physics and material science areas. Actually, let's note that a great amount of this work is actually based on theoretical models and simulations. Now let's come to the tight binding electronic structure method applied to carbon nanotubes and graphene nanoribbons. Usually one considers the reciprocal space lines, which are shown in red for the system under investigation, for instance, carbon nanotube or graphene nanoribbons, which are clearly related to the real space geometry shown in the picture above. We can use these cutting lines to cut the electronic structure of graphene along their directions, and when we consider all the obtained sections, we get the electronic structure of a metallic or a semiconducting system. The system will be metallic if one of these lines crosses the Fermi-Dirac point, that is one of the 6 corners of the graphene Brillouin zones where valence and conduction band of graphene touch in one point. Otherwise, if one of these lines doesn't cross the K point, the Fermi-Dirac point, the system will be semiconducting. In this slide, I'd like to give you a comparison of the electronic band structure of carbon nanotubes and graphene nanoribbons for both armchair and zigzag geometries. You can see that zigzag carbon nanotubes and armchair graphene nanoribbons both show a direct band gap at the center of the Brillouin zone. Hence, the critical point is K equal to 0. On the other hand, you see that armchair nanotubes are always metallic for any n, and that the Fermi point is located at 2/3 of the Brillouin zone. The situation is quite interesting for zigzag graphene nanoribbons since they show 0 energy bands at Fermi level and the appearance of edge states located between 2/3 and the edge of the Brillouin zone. Within tight binding methods, it's also possible to obtain prediction related to the dispersion relation of optical matrix elements and optical selection rules for vertical interband transitions in both carbon nanotubes and graphene nanoribbons. In particular, you can see that the optical selection rule of armchair graphene nanoribbons for both light polarization parallel or perpendicular to the main axis of the system is clearly reminiscent of the optical selection rule known for carbon nanotubes. Whereas in the case of zigzag graphene nanoribbons, the selection rule related to the polarization of the light is rotated by 90 degrees. So, optical properties are clearly important in addition to electronic density of states for predicting if an optical transition can actually be observed or not in optical spectra. So, we can say, generally speaking, that tight binding method is able to predict both electronic and optical properties of graphene-based systems with a qualitatively good agreement with experimental data. However, around 2004, there were several experimental findings which were related to the presence of strongly bound electron-hole excitation in carbon nanotubes because the low dimensionality of these systems enhances the Coulomb interactions. So it was clear that this pointed out for the need of going beyond the single particle approximation in the calculation of the electronic spectra of these systems. So far, there have been several theoretical methods, mostly ab initio methods based on many-body perturbation theory or artifact calculation with single excitation configuration interaction, which were also lately applied to graphene nanoribbons, since up to now experimental data are lacking for the optical properties of these systems. However, let's note that none of these methods takes into account electronic correlation at full many-body level of description, as it occurs, for instance, within the Hubbard model, which is a model suitable for strongly correlated electron systems with a strong Coulomb interaction, as for instance occurs with insulators. For graphene nanoribbons, I've considered the simplest formulation of the Hubbard model with just the U term for on-site Coulomb interaction added to the tight binding term, which was in the simplest case defined only for nearest neighbor opening interactions. The basis set was defined for half-filled system with on average 1 electron per sites and 0 spin polarization. However, it's well known that the main drawback for a numerical solution of the Hubbard model, actually by exact diagonalization method, shows an almost exponential increase of the number of states with the number of sites in the chosen lattice model. So we have huge matrices to be diagonalized. That's why in the latest decade, 2 methods have been devised for trying to address larger size systems: density matrix renormalization group and quantum Monte Carlo methods. However, since these methods work with a reduced Hilbert space if compared with a complete Hilbert space used in exact diagonalization, it's always good practice to check their results against those known from exact diagonalization method before trying to address larger size system. Within exact diagonalization method, one looks for a sparse matrix representation of the real space Hamiltonian mapped to a given quantum lattice model. Usually, Lanczos method and other iterative methods are employed for trying to obtain information related to the ground state and few low-lying excited eigenstates, which are clearly the most relevant object for investigating low-energy properties. For my calculation, I could rely on mathematical packages for second quantization algebra and the open source C++ ALPS libraries, which is an open source suite comprising several types of codes: exact diagonalization, density matrix renormalization group, quantum Monte Carlo, and so on. Of course, for addressing larger size system with 12 or 14 sites, I could benefit of the high-performance computer resources hosted by Cineta Consortium. Now let's come to the excited state spectra of graphene nanoribbons. In particular, here I'm considering those of armchair type as far as the age is concerned. Here you can see the basic unit cell of the armchair nanoribbon, which is repeated periodically along the ribbon edge, and which shows both A and B type carbon atoms exposed on each side of the stripe. Since we know that the tight binding method was defined for nearest neighbor open interaction, it's actually a term which describes the connectivity of the ribbon lattice. So we can perform a topological transformation from this ribbon lattice model to a brick type lattice model where I completely neglected the hexagonal symmetry of the systems. Since we are also interested into states at the center of the Brillouin zone, k equal to 0, because of the density of states and the optical properties for interband transition, again we can perform another topological transformation, fold the brick type lattice model onto itself to give a two-leg ladder models whose width is given by n. That's the number of A and B sides in the ribbon lattice model. So actually we have to perform exact diagonalization for the Haber model defined for a two-leg ladder model with uniform tight binding coupling everywhere, both inter and intra-chain. I will perform exact diagonalization for 4 kinds of ribbon geometries with the number n of AB couples between 4 and 7. So I'll consider lattice model with 8, 10, 12, and 14 sides respectively. It's well known from tight binding that the electronic band structures of armchair graphene nanoribbons can be classified into 3 families according to the way of specifying n as a function of an integer p. So we have 3 families, the 3p plus 1, 3p plus 2, and the 3p family. I was able to verify through my calculation that this family behavior also holds when electronic correlation are taken into account, for instance, for U on T non-zero. And I was able to verify that the 3p plus 2 family, which was metallic in tight binding unit, now becomes a semiconductor as well. And since the correlation parameter U on T for graphene-based systems is believed to be between 1 and 2, you can also see that the 3p plus 1 and the 3p family are almost similar to each other in this correlation range, whereas the 3p plus 2 family is the one clearly standing apart. This behavior also holds if we consider not only transition energy, but also the optical oscillator strength, the intensity of the transition, which is found also to be lower than the one calculated in zigzag carbon nanotubes. I've also performed the spin multiplicity analysis of dark states, which are optically inactive excitonic states, which are believed to play an important role in quenching the optical photoluminescence quantum field in these nanostructures. You can see that I found a few triplet states just above the ground state, and a few singlet dark states very close to the lowest bright one-photon singlet excitons. This was also found for carbon nanotubes. Now let's come to the quantum lattice model for zigzag graphene nanoribbons, which is quite different. It's a one-dimensional system with open boundary condition and alternating open to gamma 0 C, where C is a K-dependent phase factor, and gamma 0. At the Dirac point, where there is the onset of edge state, we can see that C becomes equal to 1/2, so the model greatly simplifies into an open-ended chain with uniform opening everywhere. So this is quite convenient also for performing density matrix renormalization group calculations, since this algorithm best converges for one-dimensional system with open boundary condition. And here I was able to investigate also ribbon of larger widths with chain models with up to 40 sites, and you can see that I found an inverse dependence on the ribbon width as far as the transition energies are concerned. I was also able to find that just the lowest excitonic state has the strongest oscillator strength, whereas the other two transitions have almost negligible oscillator strength. This is the excited state spectrum of a zigzag graphene nanoribbons, which shows an alternating sequence of triplet and singlet dark excitons at low energies. And I found also a very intense two-photon active state, this one, which is also more intense than the lowest bright singlet excitons. Such effect was not found for armchair nanoribbons. If we also consider the charge and spin gap, you can see again an inverse dependence on the ribbon width, whereas if we consider the dependence of this charge and spin gaps versus the correlation parameter U1T, you can see that the charge gap grows with U1T, so the system is driven from a semiconducting, into an isolated regime, whereas the spin gap decreases with U1T, so the system becomes more subjected to magnetic excitation. Such fact can be relevant for devising spin filtering application based on the half-metallic behavior of zigzag graphene nanoribbons. Finally, I'd like to outline a few directions for further research work. First of all, an in-depth analysis of the many body wave functions should be performed for addressing the spatial profile of excitons and related spin polarization. And in order to do this task, we should rely on appropriate correlation function for excitons, for addressing, for instance, the weight of specific excitonic configuration like unbound of Holland double, unbounding Holland double pair, that is singly bound excitons, B excitons, and so on. Of course, it would be certainly interesting to address other edge states and ribbons with different edge geometries, since now, thanks to this paper, we also have a classification of the range of existence of edge states in reciprocal space based on the geometry of the edge ribbon. So to conclude with, I'd like to thank Professor Matthias Stroyer for helping me with these ALPS libraries for exact diagonalization and porting my codes on Cineca high-performance computers, and Professor Jan McCulloch for helping me recently with his matrix product toolkit, which I use for DMRG calculation based for zigzag graphene nanoribbons, which I've shown you today for the first time. And of course, thank you all for your kind attention.
questions?
Did you try to use DFT theory to calculate?
Not at all, because my purpose was to go beyond DFT, because within DFT you have, let's say, a mean field description. Perhaps you could use DFT with GW approximation and that Staffordshire equation, which was hinted at in some slide above, but that was not my task because there are already many papers about that. So my purpose is to use the techniques for strongly correlated electron systems, for insulators, but let's say that now you find many papers dealing with Haber model applied to graphene. Actually, there is also a phase diagram within quantum Monte Carlo and Haber model for graphene. So it's important to see beyond mean field theory, take into account quantum fluctuations at full many body level correlation, even if we are, let's say, in a low intermediate correlation range. So that's why I find a certain agreement with the FT calculation, because the electronic correlation within graphene are not so strong as it is supposed to be, since the density of states is practically zero, because if you consider that, but in the case of graphene nanoribbons, you have to consider that we are in low-dimensional system, not truly a two-dimensional system, but they show the appearance of gaps because of the confinement. So that's still different. Thank you. Thank you.
Any other questions? If not, let's thank Jessica again.
Thank you.
So next speaker is Francesco Flores.
So, good morning. Okay. So, my name is Francesco Flores, and I am a PhD student in Pavia. Concerning my thesis, I'm working with many different people. Franco Marabelli, that is my advisor, Maddalena Patrini and Lucia Fornasari, and I have also a collaboration with the University of Cagliari, and I want to thank in particular Francesco Floris, Cristiana Figus, Giovanni Bongiovanni, and Andrea Mura. And last but not least, I'm working on some project that concerns the Joint Research Center of the European Commission. In particular, we study how to make measurements on foods and drug deliveries and nanomedicine, and so we have a spin-off between the JRC and my group, and it's called Plasmor, and I want to say thank to Paola Pellecani and Andrea Valsesia. Now I will show you a small part of my research, and in particular I will show you something concerning plasmonic structures. So, as I told you before, I came from Pavia, and it's a quite small city in the north of Italy, and the other one is Cagliari. So if you want to come, it's a great place. But in particular Cagliari in this season, because we have a long beach, and you can have fun after that you spend maybe some years in a place like Pavia. It's quite different, and it's an improvement that makes the difference. So let's start with some more serious things. What plasmonics? So plasmons are essentially a coherent excitation of the free electrons that you can find in a metal, when the metal is in touch with a dielectric, and at the surface you impinge with an electric field. So what you can see is that the charge starts oscillating, and in this case we have two nanoparticles, the impinging field, and since the charge stays localized in the particle, you have the so-called localized plasmon. If you have a different configuration, for example, two slabs, a dielectric slab and a metal slab, you can excitate a wave at the surface that can travel among the surface, and so it's called propagating surface plasmon polaritons. But humans know plasmons even because you can find them in nature. Physics means nature in ancient Greek, and nanoparticles are used by these butterflies on her wings in order to achieve these marvelous colors that you can see, and so they are great. We can use it, we can understand it, and we decided to make some analysis concerning these plasmons and plasmonic devices in order to achieve an application that enables us to make sensing. How? In a very simple way. So we used a glass substrate. We have a polymer that we deposit on it, and then we spatter on top gold. In this way, we have polymer pillars, that is our dielectric, as I showed before, and then between the pillars we have gold. At the interface between gold and the polymer, and in addition between gold and, for example, air on top, you can construct, if you imagine this in three-dimensional, here a ring that is called a ring resonator, and plasmons, so electrons, can run along these rings. You have a squeezing of the electromagnetic field in something like donuts, and this donuts made of electrons running is very useful in order to calculate the differences in the refractive index that you can introduce on the top of the surface. For example, we have a patent for this structure, and maybe you can find other information in our publication. This is an AFM image of our surfaces. So here you can see the morphological structure. This is the gold, and these are the pillars. Here we have a different kind of image that help us to understand where you can find gold and where you can find the pillars. It's called phase image. And here you can see a 3D reconstruction of the surface. Here you see the gold, and these are the pillars with their head. In addition, since we wanted to understand where these resonances were placed in the structure, we made some simulation, and we tried to find how to tune this plasmonic resonance, changing the morphological parameters. The ring, the answer in the ring that I showed you before, this, is if I illuminate the structure from the substrate, I can collect the reflected light, and when the light has the proper energy, is absorbed by the plasmon. All the electrons absorb just as one single particle, all the energy, and you can see a dip in the reflectance response. It's quite important because if you change the refractive index in the environment of the top of the pillar, you can shift the resonance. So the position in which you find the minimum in reflectance is moved. In this case, we try to coat the surface with a glass, sol gel glass. We put on top 5 nanometers of sol gel glass, Theos, in particular, theta-hydroxysilane, and we saw that the resonance is shifted. 5 nanometers of glass means a red shift of more or less 38 nanometers. Last, we made some simulation concerning the electric field because we wanted to understand if we can achieve even a squeezing of the field. This is the gold. Here we have the pillar, and here on top we have air. As you can see, the field is squeezed here. This is the ring resonator. If you put some glass on top, you increase the refractive index, you squeeze the field between the gold and now the glass on top, and then you have air, and you can achieve a squeezing and an improvement in the density of the electric field. Next step, we wanted to apply this. We need to use this system to make measurements that can be useful to, first of all, foods, because we want to understand, for example, if the food that we are eating is safe or not. SPR is one of the most useful techniques because it's quite simple to result, it's quick. Then you can use it as multiplexing, so with one chip, with one structure, you can perform simultaneously thousands of measurements on different, for example, foods, on looking for different molecules or pollutants. It's flexible, low cost, robust, it's very sensitive because you can measure changes in the refractive index low down until 10 at the minus 6, and it's quite portable. This is the system. We have the patent. If you want, you can buy it on the internet, and then you can use it in your labs. Essentially, we have a LED that we use to illuminate the sample. Here, this is the substrate, the pillars, and we have a fluidic system in order to flow on top what we want to measure. And then we collect it with a sensitive camera, exactly the same camera that you have in your phone. This is our study concerning the sensitivity. In this case, we considered water and water with salt with a concentration of 2%. Here you can see the shift that is quite small, but if you use the ratio between these two signals, you can achieve this kind of structure that is a relative measurement, and this is our signaling amplitude. This means this is the shift, and this is the intensity of the shift. So if you have a shift, you have something. So you can see, you can say that there's something in what you are measuring. If you calculate the height of the signal, you can say how much of this pink there are in what you are measuring.
So you don't measure the shift in wavelength? You don't measure the shift in wavelength?
Yes, we measure it.
It's quite sensitive here.
Yes, 10 at the minus 6. We arrive at 10 at the minus 6, and the problem is that you start calculating the fluctuation that come in the refractive index by the fluctuation of temperature. So if you want to go further, you need a cryostat, you need to control pressure, you need to control temperature. But here we want just to make measurement at room temperature and at room pressure. So, step further, we started with biological application and with medical application. Here you can see the structure that was functionalized in different ways. Here, in order to make the study of sepsis marker, we functionalize different arrays of pillars, and then we make the measure. In this way, you can have a negative control that are the pillars that are not functionalized, so the resonance is not shifted, while here we functionalize by this ABPTX3, that is a molecule able to couple with sepsis, and if you have sepsis in what you are measuring, this attach on that molecule, then you see a shift and you can measure the buffer and the signals. Another key point is the multiplexing. So here we have the pillars and we can functionalize different pillars with different molecules. So we can detect in the same time different molecules. And since the SP is quite quick, we can do it in something like 200 seconds. It's quite useful because you don't have to wait for a chemical analysis. Imagine water. You know in a couple of minutes if your water is safe or not, if you can drink it or not. As a proof of concept, we try to apply the multiplexing to frozen adulteration of milk, and we try it to the goat milk that has inside a particular protein that is called K-casein, and sometimes it is adulterated with cow's milk, and you can find a typical marker that is called gentamicin. So we functionalize different pillars with, in one case, gentamicin, in another K-casein, and we made the measurement. These are called sensograms, and by the sensograms, you can see that you have different colors. The colors tells you if inside the goat milk you have cow's milk, because you can see if in your K-casein there is gentamicin. But the story goes on. As I told you before, this is in collaboration with Cagliari, we coat the surface with a sol gel thin film for several purposes. The first is to protect the surface. The second is that you can wash the surface and come back to initial performance, so you can reuse it, because polymers usually eat what you put on its surface. And then is that you can use this thin film as a matrix, and you can disperse the proper, for example, fluorophores. The idea was to use, in the first case, this coating as a matrix, and we dispersed rhodamine, and our results was that if you have the rhodamine in touch with the gold, you have the quenching of the defluorescence. So gold attract the electron that in rhodamine can give you the fluorescence, and it's quenched. While if you use a small tick of glass on top, you can divide the rhodamine from the surface, but since you have 4, 5, 6 nanometers of glass and a penetration depth of your plasmon or 30, 35 nanometers, you can use the plasmon to pump the rhodamine, and you see an increase of the fluorescence signal. Vice versa, if you want to use it as cells, you want the gold to pump your Raman signal. So you have to put the rhodamine in touch with the gold. The gold can pump the rhodamine, and you can see an increase in the Raman signal. Here you can find the signal, the Raman signal of rhodamine on top of the glass, because it was 0. So I just showed the rhodamine in liquid solution, and the rhodamine in touch with the folder. So the take-home message is that we studied from the beginning a plasmonic structure that we wanted to be able to support proper plasmonic resonances, and we characterized it with structural and via structural and optical measurements. We made even FTTD, finite difference time domain numerical simulation in order to understand how this structure works. And our applications are at the present the SPR sensing with a nanoplasminics device, and future is maybe Raman and photoluminescence sensing. Thank you very much for your attention.
Thank you. So any questions?
Yes, you are quite interesting.
Yes. Just a curiosity, how much does it cost? You're saying it's the
So, yes, it's very cheap, and we wanted it cheap for different reasons. All the devices, it's 1,000 euros. But we are working on, this is quite big, because this is the first beta version. But now we have another version that is more or less 15 centimeters, 10 and 3. And the cost is more or less 500 euros. And the chip, if you want to change it, is 20 euros.
And how much does it take for the plasmonic structure to, how many times can I use it, and if it has like a...
Okay, if you use the cover one, we made measurements for using the same structure for 6 months, and we used it, I don't know, maybe 30 times. You wash it with ethanol, or you can change the precursor. Instead of Theos, you can use a mixed precursor with, for example, Titan inside, and then you can wash using even acid as HCl. And we don't know much, but in principle, you can use it thousands of times. It depends. In the end, you start to degrade the polymer, but we didn't write it yet. It's normal. But you can change it because you need 20 euros to change it. If you use it with, for example, water, with proper molecules as scalants, in order to analyze heavy metals in water or something like that, you can use it maybe years, I don't know. But when you put it out, you wash with ethanol, and it's new.
It doesn't evaporate.
No. And you can touch with your hands without any problem. You can put it on the table, take it, and put it inside. It's very robust.
Thank you.
Any other question? If not, let's thank Francesco again. We now have Maria Barbara Maccioni from the University of Padua.
So good morning, everybody. And I'm Maria Barbara Maccioni, and I'm a PhD student at the University of Cagliari. I've studied the structure and electronic properties of gallium oxide and interface in collaboration with Francesco Ricci, Alessio Filippetti, and Vincenzo Ferrettini, my research group. Our research topic are methods for ab initio calculation on correlated materials, to study the magnetic properties and electronic structure and transport at the oxide interface, and optical and electronic properties on novel semiconducting oxide. We used the density functional theory with pseudo self-interaction correction and Lewis model. We used different codes, Vienna Benizio simulation package, Quantum Espresso, and PWC ultrasoft code. So the monoclinic gallium oxide is a chemically and thermally stable compound with an high optical band gap. So it's a transparent conducting oxide. So it's a promising candidate for application mainly in high-powered transport device and optical limiters for the ultraviolet high temperature stable gas sensor. We start with two calculation of electronic properties like structural parameter, band structure, and density of states of gallium oxide. And in final, we have doping this compound to tune the band gap for the possible application in power devices. The gallium oxide has different phases, and the more stable is a monoclinic. It belongs Pesa group C2M and has 20 atoms for unit cell. There are two types of gallium in octahedra and tetrahedra combination. As you can see, the crystalline structure can be seen with a double chain of edge sharing octahedra linked by a chain of tetrahedra combination in B direction. We have used the DFT theory as implemented in the basket code, and we have utilized the GGA approximation, the generalized gradient approximation for the part of electron-electron interaction, and we have utilized this potential for the electron-ion interaction. This picture shows the band structure of gallium oxide in the structure with 12 atoms. There are a direct gap at gamma point and indirect gap at V and L prime point. The maximum of valence band is very flat, but is slightly higher is found compared with a gamma point. As you can see in this picture that shows the total density of states and the projected dose for gallium, and this for the oxygen. The valence band is mainly constituted by P2S states of oxygen, and here are the conduction band is mainly formed by 4s states of gallium. The GGA approximation underestimate the gap. In fact, these values are corrected by a semi-empirical correction that depend on the dielectric constant. In this slide, I show you the variation of gap energy with the volume for two methods, the SIC and hybrid methods. The gap with the first method is in good agreement with experimental data, but the hybrid is don't work very well. But both show a linear trend and with the volume, and it's very insensitive to internal structure, but depend on only mainly on the volume. This is the task plot for direct gap absorption that show three different one set. This shows the polarization isotropy for when the light polarization is parallel to optical axis, the d-axis. The prediction is confirmed in experimental experiments at the University of Parma. To tune the band gap of the gallium oxide, I've considered indium, and then indium oxide that is have a big split phase in which indium has a six-fold and four-fold coordination. We have started with the studying in optimization in volume and internal parameter to structure with indium with the substitution of indium for the gallium in different possible tetrahedra and octahedra sites. We found that in the tetrahedra site the cost is very huge, but the lower energy are in this configuration. So we have optimized for several configuration concentration of indium, and I've calculated the gap in function of indium concentration. The direct gap and the volume, okay, show both a linear trend, and the variation is calculated is in agreement with the experimental data. So the last point is the study on interface. The study the offset at heterojunction. In general, this offset is described by the energy discontinuities and electrostatic potential at interface. The total discontinuities is divided between the valence and conduction band discontinuity described by formulas. In general, we have different band alignment, and for example, the straddling gap, the staggered, and the broken gap. So in the interface with between gallium oxide and gallium oxide dot with 12 una concentration of indium or to 12%, we obtain two different band alignment depend on the arrangement. This is the configuration in which all the structure is relaxed in volume and within internal parameter. But this is the case in which the gallium dot is epitaxially with the gallium oxide. So it means that the lattice parameter are the same of the gallium oxide. In the interface with gallium oxide doping with 6% of indium, we have a potential very lower than the interface before, but there are a reverse staggered alignment in comparison with the other preview. In conclusion, the first principle calculation provides usable information for electronic and structural properties of the gallium oxide and alloy. The gallium oxide is a semiconductor with a weighted solution once at 5 electron volt. That depends on the polarization. We have tuned the band gap with the substitution indium for gallium at a low concentration, and indium gallium oxide epitaxially on gallium oxide as show a staggered interface band alignment.
Any questions? You should stay first.
Just a curiosity about. So you started with a gallium oxide structure that had 12 atoms, right?
Okay.
Okay,
Yes.
right. Okay. When you substituted the gallium with indium, your structure has
It's very, it's more bigger.
okay.
Okay.
So you make a supercell.
Yes, a supercell with 80 atoms, like the structure of indium oxide. We calculate the structure, the properties to supercell of gallium oxide.
Yes, because when you increase the volume, the band gap decreases. Right.
Yes.
Okay, thank you.
Any other questions? It's not. So thank you again. Now, Sofia Mazzani.
So good morning, everyone. Thank you for the organization to let me participate in this event. My name is Sofia Pazzagli, and I'm going to discuss the energy transfer from a single organic molecule to a graphene monolayer. This topic is part of my master thesis project that I did in Lens, which is the European Laboratory for Nonlinear Spectroscopy that is located in Florence, and which research activity covers 4 different areas. In particular, the group that I did my master thesis and where I am currently working belongs to the photonic area and is guided by Costanza Toninelli. Our research focuses on the study by optical means of the combination of an organic molecule-based single photon source with different photonic nanostructure in order to develop novel light matter interfaces for quantum technologies and for application ranging from fluorescence-based sensing to solid-state protocol for quantum communication. As a starting point of this presentation, I just recall what Francesco was saying in a different way, and I'm starting from a simple 2-level system, an excited 2-level system. The spontaneous emission decay rate of this 2-level system is given by the Fleming-Gordon rule, and is written in terms of the transition matrix element from the excited to the ground state, and given by also the density of the final state at the transition frequency. This term, in particular, is determined by the dielectric environment in which the emitter is embedded. This means that spontaneous emission is a property of the coupled system emitter plus environment, rather than an intrinsic property of the emitter. That's what we were saying also before. So, already having a simple configuration like a planar interface between 2 different dielectric material is sufficient to change the optical properties of a nearby emitter, especially when you are in the so-called near field regime, which means that the distance between the emitter and the interface is much smaller than the wavelength, the emission wavelength of the emitter. What we will see is that in this situation, there are available new no-radiative decay channels for the molecule, and thus the spontaneous emission decay rate is affected, and also the lifetime of the emitter, and the quantum yield, which is related to the fluorescence intensity. So the emitter the fluorescence of the emitter is quenched. And this, of course, with respect to the case of the same emitter in a homogeneous dielectric. In my case, in this study, what I do is that I will start giving a brief description of my emitter system, which is made, of course, of organic molecule embedded in a crystal, and I position this emitter on top of a graphene monolayer. And I also will give you some brief information about what is graphene and its application in nanophotonics. After this, I will focus on the coupled system emitter and graphene, and let you see that in this case, the dominant relaxation mechanism is the energy transfer from the excited molecule to graphene. I will give you a brief, really few words on the theoretical model that describes this mechanism, then introduce the experiment setup that we use it for test this mechanism, and then I will discuss the result. So our emitter is made of organic molecules, dependent rilene, embedded as impurities in anthracis. This die-host pair is pretty recent and has an energy level scheme modeled like a three-level system. It is found to be a really bright photon sources in the near infrared with an emission at around 785 nanometers, both stable photon sources, both at room and low temperature. And since the probability to relapse, to decay in the triplet state is really low, usually we can approximate our molecule as a two-level system. Another noteworthy property of this system is the pretty easy fabrication process, which is called spin coating, from which that you start from a drop of the solution of DBT anthracene, then you put it in the spin coater, it rotates, and you finally obtain a crystal that is really thin, actually. You obtain also on average with 50 nanometer of thickness, which ensures our system to be in the near field regime. So we can study coupling mechanism in the system. All these properties makes the system, as I said, really promising for application in nanophotonics, as proposed by Huang and colleagues, that they propose a logic gate scheme in which a molecule is just positioned on a nanostructure, a microfabricated optical waveguide, and I mean, that's the logic gate. Concerning graphene, I think I lost the first presentation, but I think that we introduced graphene, of course, you maybe know it, is the first 2D material stable at room temperature. Is pretty recent, but still it's really emerging and gaining a lot of attention because it's really particular. And this particularities and incredible properties derive from its dispersion curve, energy band structure, actually, that is shown here, and that especially is a gap-based band structure, and in the low energy range with respect to the Fermi energy, it can be it assumes a conic shape, and the dispersion curve becomes linear. These are just few of the incredible properties that graphene has. It is transparent and is a thin conductor. It's really robust. It's really easily integrable. And concerning optical properties, it has a broadband. It is a broadband light absorber, and its optical properties are tunable, both chemically and electrically. Here I just report two prototypes already, proposed, and I think some of them are already also developed, of broadband optical modulator and a high gain photodetector. Okay, now that I just present the two different elements of my tablet system, I put it together, and as I said before, what happened is that we have energy transfer from the excited molecule to graphene. Energy transfer is a very, it's a pretty well known, at least for who is working with this stuff, mechanism. It's known since 70. And usually it's used to describe the interaction between two fluorescent molecules. You have an excited one, that is the donor, and you have an unexcited one, which is the acceptor. If these two molecules are sufficiently near to one another, and if the emission spectrum of the donor overlaps the absorption spectrum of the acceptor, then you have energy transfer. This mechanism can be modeled with a dipole-dipole interaction, in which the dipole corresponds to the electronic transition of your molecule, and thus has this shape. No? The transfer energy efficiency has this shape, with scales with the 6th power of the distance between the two molecules. In our case, what we have graphene, and then we have our system made of several molecules. Let's consider just one molecule. What we have, we can consider it all molecules. No, never mind. What we have here is that we can treat this mechanism as a fret-like mechanism, so as the Forster model I presented before. Here you have the emission spectrum at room temperature, which is our experimental condition of the system. And this is the absorption spectrum of graphene. We have overlap of the two, so we can have energy transfer. And actually the distance, as I said before, we are at 50 nanometer at max from graphene, so we are in the near field. And we can have energy transfer. In this case, we have to consider that we don't have just one dipole, which in the case of graphene corresponds to the electron-hole pair that is appear in graphene when it absorbs energy from the molecule, but we have a surface of dipole. So the energy transfer efficiency scales with the 4th power of the distance. I don't get into the detail of the model, as I said, but Blanco et al. Proposed to model this interaction and going to calculate the power radiated by the electric dipole, oscillating the electric dipole, that is forced by the reflected field from graphene. So the dipole is placed on top of graphene, and it radiates, and its radiation is reflected by graphene, and then you go and calculate the interference effect of the emitted and reflected field. What you get is this kind of expression, in which you have the spontaneous emission decay rate in the case of graphene, written in terms of mainly, you have the fine structural constant, you have the emission wavelength of the emitter, you have the distance, of course, and then you have the permittivity of the substrate and of anthracene, which is the embedding material of the emitter, and then you have the spontaneous emission decay rate of the emitter without graphene. This law is a universal distance scaling law because it depends only on the distance. All the other parameters are fixed. This is quite interesting because it's, as we will see later on, it has many possible application. So, to study the energy transfer mechanism, what we do is to measure the lifetime of our emitter and as it's correlated to the distance. What we expected is that since we have a new non-additive mechanism available for the emitter, is that its lifetime will be lowered by the presence of the graphene. And the more the molecule is near to graphene, the shorter is its lifetime. So the best way would be that we have one molecule and we change its distance with continuity from graphene. Of course, our system doesn't allow this, and so we did a statistical analysis, acquiring lifetime measurement on several molecules, and of course, what we need to know, what we should do, was to make single molecule spectroscopy, so measuring each molecule at a time. Just a few words on the principle of our setup, that is mainly a home-built epifluorescence confocal microscope. Confocal, I think, is the same that you have, of course. The basic principle of fluorescence microscopy is that fluorescence is redshifted with respect to the excitation wavelength. So you can spectrally separate excitation from the fluorescence. So what you do is that you excite your system, you put a dichroic filter or whatever else, just separate the two wavelengths, and then you detect it. In order to be focused on really a small volume of your system, in order to make single molecule detection and study each molecule with respect to no another, so it's just the specific properties of that molecule, you just insert in the detection line a special filter, a pinhole, like this one. So what you do is that you cut all light that is coming from, not from the focal plane, okay? And the nice thing of this system is that you can, of course, move, in our case, we move the sample, so we can move the sample up and down on the X, Y, and Z position, and build up a complete 3D map of the system. So this is this, no, okay, this figure is just to show you what's the difference between a normal microscope, a wide field fluorescence microscope, and the confocal one. I don't know if you can, but I think you can see that it's the resolution is much higher here, because it's limited only by the Abbe criterion, which is the diffraction limit, okay? So just other diffraction limit resolution, quite nice. This is a sketch of the setup. I don't get into details. So we had several laser sources, several detectors, so we can make with the same setup all the characterization of the sample and the complete study of this system. I just report here a few images just to let you know how does this system looks like. This is a crystal of anthracene. We can make it like with a white light in the excitation and the CCD camera. Then you just switch it, just put on a flippable mirror, so it's really easy, and you have the fluorescence image of what's going on. In order to have a much nicer image and to point each molecule at a time, we made a scan, a confocal scan, just moving the nanocube on which the sample is mounted, and you can build up a map of an area of the crystal. Okay, once you have this, you can pinpoint, you can just choose a single molecule, focus on top of it, and make lifetime measurement. What we use is a pulsed source and a TCFPC unit, and we make time correlated single photon counting, which is the most common technique to build up the fluorescence decay of a signal. So here we have two examples of a decay of two different molecules, and we fit this decay with a single exponential decay, which is this law, and considering the background fluorescence that you always have to consider. So from this fitting procedure, we determine the lifetime of each emitter, and then we build up histograms. Okay, so from our sample, we collected lifetimes of 150 molecules, and this is the histogram of the distribution of lifetime obtained with the probability. We also make a reference sample with our graphene to see what is changing. And what we observe is that it's quite evident. No? You can see that here, in the case of no graphene, the lifetime distribution is symmetric and is around 4.2 nanoseconds. When you put graphene, what happens is that, as you expected, depending on the distance from the surface, you can go really at low lifetime. Okay, so you would expect that these kind of molecules are really near graphene. To make a bit more quantitative interpretation of this result, we just take the model, as I presented before, and we just put inside all our parameters specific of the system. And this red curve, that now it's, I put it in a very bad way, but I can assure you that it's in good agreement with the experimental result. So what we did is something that it confirms a theory that is well working actually in other systems as well. So to conclude, what we did, we studied the energy transfer mechanism between this emitter, DBT molecules in anthracene crystal, to graphene, this 2D material. We did this a quantitative study, making lifetime measurement with this confocal on-built confocal microscope, and we compared the result with theory, finding good agreement. As lifetime is related to the distance from graphene, this system can be seen as a prototype of a nanoruler, which is a ruler that is able to measure nanoscopic distance. We made a simulation on the best thing that we can obtain with our system, and what we see is that we can have a graphene-based nanoruler made with our emitter that will allow to measure distances up to 30 nanometer with an uncertainty less than 5 nanometer. Thank you for your attention.
So, any questions, comments?
Ce le rimpalliamo. È giusto? Sorry.
Yes, just because I understand. So the first question is that you show the inter-system crossing in the slide. So I wanted to ask if you evaluate the triplet.
Yes, we did. I mean, it's sorry. Continue.
And maybe the consequences of transfer energy from the singlet to the triplet.
Actually, we didn't did. I mean, my supervisor, she worked with these molecules since the beginning, so they did all the characterization of the system. And so far, it's 10 to the minus 6, the probability to go to the triplet, to decay into the triplet state. And that's because anthracene is a really good host matrix for these molecules. And what was the other question?
No, this was the first.
Okay.
The second I had two.
Sorry.
The second was not really concerned with this. With the triplet, can you extricate polars on graphene?
Actually, my other colleague in the group, she's studying, yes, she's studying this. Of course, depending on the substrate that you put on it.
Okay, yes, perfect. So, did you perform no measurements?
Yes.
And what did you find?
I don't know.
So,
but we are doing it. Actually, we don't have our own. We have to ask for other people for the devices to make the measurement.
Any other questions or comments? No, that's thanks. Very good.